we do still show those lone pairs. One would be off to the right and one would be off to the left. Yeah, that looks a little bit weird. Hello, OChemNinjas. In this video, we're going to look at Newman projections in 5 Ninja levels, starting at Ninja level 1 and working our way up to Ninja level 5 Newman projection. Ninja level 1 is your standard staggered and eclipsed Newman projection. These are about as standard and textbook of Newman projections as you're going to see. So much so that I've developed a 3-step foolproof plan for drawing standard, staggered, and eclipsed Newman projections. If you'd like more information, I have a video linked down below. We draw standard, staggered, and eclipsed Newman projections in our standard Newman projection way. We start with the dot and the circle. Giving the molecule a numbering system and choosing which side of the molecule to look at tells us that carbon number 2 is the carbon in front and carbon number 3 is this carbon in the back that we can't quite see. For the standard staggered Newman projection, carbon number 1 is in the southern hemisphere attached to carbon number 2, and it is in the vertical axis because it's in the plane. If I'm looking at this molecule from the left, that bromine group will be on the right side of the Newman projection in the northern hemisphere attached to the front carbon, so it will be here to the right, and that hydrogen will be pointed to the left. Carbon number 4 is attached to the back carbon. It's up in the northern hemisphere, and it's on the vertical axis because it's in the plane of the page, so the carbon number 4 is here on the top of our Newman projection. The chlorine, if I'm looking at the molecule from the left, that chlorine is going to end up on the left side of my Newman projection. So it'll be down in the southern hemisphere attached to the back carbon is the chlorine, and the deuterium is attached to the right side of the Newman projection on the back carbon. Standard staggered Newman projection. The eclipsed version works exactly the same way. Carbon number 1 is attached to the front carbon. It's down in the southern hemisphere, and it is on the vertical axis of the Newman projection because it's in the plane of the page. So carbon number 1 is here on the bottom. If I'm looking at this Newman projection from the left, that nitrogen group will end up on the left side of my Newman projection. So it will be here in the northern hemisphere attached to carbon number 2. And if I'm looking at it from the left, that hydrogen will end up on the right side of my Newman projection up in the northern hemisphere attached to the front carbon. Carbon number 4 is attached to the back carbon. It's down in the southern hemisphere. It's attached to carbon number 3, and it's in that vertical axis. That makes it eclipsed with carbon number 1. So don't forget, we just offset the bond a little bit. Here is carbon number 4, and we draw that line as if it were going all the way to the center of the molecule. We don't make that line vertical. If I'm looking at this molecule from the left side, that oxygen is going to end up on the right side of my Newman projection. It's going to be eclipsed with hydrogen. So again, we offset just a little bit, and here is that OH group. The hydrogen will be on the left side, eclipsed with the nitrogen. So here is that hydrogen. This is the standard eclipsed Newman projection. This is Ninja level 1 in this series. We should get pretty comfortable with drawing these types of Newman projections fairly quickly and fairly accurately. Ninja level 2 deals with Newman projections that have extra stereocenters in the molecule. You may not have gotten to stereocenters yet in your course. Stereocenters just means extra wedge and dash groups outside of the 2 carbons you're using for your Newman projection. If I were to draw this Newman projection looking down the 2-3 bond, I could do that fairly easily, but what do I do about carbon 5 when it comes up later? Before we worry about that though, let's get the rest of the Newman projection drawn in. Here is the rest of that Newman projection. The OH on the front carbon is off to the right. The OH on the back carbon is off to the left. Carbon number 4 is attached to that back carbon up in the northern hemisphere. Now we just need to add carbons 5 and 6 and figure out how to add this wedged oxygen group. First thing to do, go ahead and add carbons 5 and 6. Keep your regular line angle structure conventions. We'll draw carbon 5 up to the right and carbon 6 down to the right. We wouldn't make weird bond angles or anything like that. We would just continue drawing carbon 5 and carbon 6 to finish out the structure. Now we need to add this oxygen. It's not quite as simple as just adding a wedged oxygen because we're rotating this molecule in 3-dimensional space. That oxygen may end up on a wedge when it goes up here, or it may end up rotating onto a dash. This is about doing bond rotations and manipulating molecules. If you need a little bit of help with that, I have an entire playlist on how to manipulate molecules that I'll link to down below. What I notice is that 4, 5, and 6 are both chains going left to right in both of these structures. In the original structure, the carbon 5 was kind of an angle pointed down, and in my Newman projection, when I redrew it, carbon 5 is now an angle pointed up. To get carbon 5 from pointing down to pointing up, I must have done a 180-degree pancake flip of this carbon in order to get it in the correct orientation in the new Newman projection. And if I'm doing a 180-degree rotation of carbon number 5, that's going to flip the wedge dash notation of that oxygen. If that OH group was pointed towards you in the original structure, when we flip it 180 degrees, now it will be pointed away from you on a dash. So when I draw this OH group on carbon number 5, I will need to flip its configuration to be a dashed OH group rather than the original wedged OH group. Is that a general rule? Every time we have a wedge in the original, it goes to a dash in the new Newman projection? No, of course not. You'll need to treat every case a little bit differently. Sometimes it'll be a steering wheel rotation to bring the group in place. Sometimes it'll be a pancake flip. So you just need to check every time to see how you're manipulating the OH group or whatever group into the new Newman projection. Again, check out my videos on manipulating molecules if you'd like some general guidelines there. When we have extra stereocenters or extra wedges and dashes in our structure, we just have to be a little bit more careful when we draw the Newman projection. Ninja level 3 is when we have a heteroatom as part of our Newman projection. And I don't mean a heteroatom as part of the periphery of the Newman projection. I mean a heteroatom as part of one of the bonds that you're looking down. Why would you ever want to look down a bond like this? Well, when you get to biochemistry, you're going to be looking at protein chains a lot. Protein chains are made up of repeating amide units down the chain. One of the interesting parts of biochemistry is looking at the three-dimensional shape of that protein. In nature, that protein chain is not really linear in a one-dimensional line. It folds up into itself into a three-dimensional shape. That means these bonds rotate with respect to each other in order to fold it into that three-dimensional shape. So looking at the dihedral angles between some of those groups can actually be very useful and tell you a lot of interesting things about your protein in biochemistry. To do that, you might need to look down one of the nitrogen-carbon bonds. Drawing a Newman projection with a heteroatom is odd, but it actually really isn't all that different. We'll still start with our dot in our circle, but instead of a dot in the middle, we're looking at the oxygen. So we would put the oxygen atom in the middle of the Newman projection. Adding the rest of the groups really isn't that different than our other process. Carbon number 1 is in the southern hemisphere. It's attached to the front oxygen, and it's going to be in the vertical axis since it's in the plane. So we'll draw a vertical line straight down from the oxygen showing carbon number 1. What else is attached to that oxygen? Well, there are 2 lone pairs attached to that oxygen, and this oxygen is sp3 hybridized. So one of those lone pairs will be pointed towards you as the viewer, the other lone pair will be pointed away from you as a viewer, almost as if those lone pairs were on wedges and dashes, though we would never really draw wedges and dashes for them. But when we have a heteroatom as part of our Newman projection, we do still show those lone pairs. One would be off to the right, and one would be off to the left. Yeah, that looks a little bit weird, but this is how we would draw this for a Newman projection. The back carbon is just like any other carbon. Carbon number 4 is in the northern hemisphere in the plane, so it'll be up here on the top of the Newman projection. Looking at the molecule from the left, the OCH3 group will be off to the right side of this structure, and the implied hydrogen will be off to the left. This is the complete Newman projection for this molecule, looking down that oxygen as part of the Newman projection. Also, I'll just take this time to give you a little OChemNinja trivia knowledge. Consider the bond between this OCH3 group and the back carbon that we can't see. The carbon and oxygen are bound together through a sigma bond, so we can draw in that sigma bonding orbital around the carbon and oxygen. That carbon-oxygen bonding orbital is behind that disk of our Newman projection, so we can't see the whole thing, but it would be encompassing the carbon in the back and that oxygen of the OCH3 group. But what's actually more interesting is the orientation of the sigma star antibonding orbital. The antibonding orbital is 180 degrees opposed to the sigma bond, so we could draw in the lobes for the sigma antibonding orbital as well. Again, part of that lobe is behind the disk of the Newman projection, but it sticks out for either side of the carbon-oxygen bond. And now, here's the cool part. Notice that on the front oxygen, this lone pair off to the left is perfectly parallel with that sigma star antibonding orbital of the back CO sigma bond. This front lone pair can lean over a little bit and share some of its electron density with that empty sigma star orbital in the back. And whenever we can spread out electron density, we make those electrons more stable, which makes the whole molecule more stable. This is referred to as the anomeric effect. It was actually a big part of my PhD research. When a heteroatom with a lone pair is adjacent to and perfectly parallel with a sigma star antibonding orbital with a different heteroatom, that allows the electron density to spread out a little bit and makes the whole molecule more stable. This is a stabilizing interaction for this molecule. And again, the Newman projection allows us to see that a little bit more easily, even though it's a little bit awkward looking down the oxygen bond. That's neither here nor there for Newman projections, but it's a little bit of OChemNinja trivia for you. Ninja level 4 is where one or both of the atoms are sp2 hybridized. Both atoms don't have to be sp2 hybridized. You could be looking down a sigma bond where only one of the atoms is sp2 hybridized, or the sp2 hybridized atom might be an oxygen or a nitrogen. Like the previous example, it may look a little bit weird, but the process is actually exactly the same. In fact, go ahead, pause the video right now, see if you can draw the Newman projection for this molecule, even though we haven't gone over how to do it yet. As always, we'll start with our dot and circle. Because we're choosing to look at it from the left, carbon 2 is the atom that's closer to you as the viewer. From here, we really just follow all of the same rules that we normally follow. Carbon number 1 is attached to the front carbon in the southern hemisphere, and it's in the plane of the page. So it'll be attached to carbon number 2 in the southern hemisphere and on the vertical axis, just like it normally would be. But what about that hydrogen? Don't worry about the fact that it's sp2 hybridized. What about the hydrogen? The hydrogen is in the northern hemisphere. It's attached to the front carbon, and it's in the plane of the screen. So hydrogen is going to be attached to carbon number 2 in the northern hemisphere on the vertical axis. Yeah, it looks weird, but it follows all the same rules from our regular Newman projection drawing. In fact, when you think about it, carbon number 2 and 3 are sp2 hybridized, so they're flat trigonal planar. That means carbon 1, carbon 4, and the 2 hydrogens are all coplanar with carbons 2 and 3. So when we reorient ourselves to look at it from the left, if everything is coplanar and everything's in the plane of the screen, the hydrogen's sticking straight up and the carbon is sticking straight down. It actually follows quite nicely. Adding carbon number 4 is the same. It's in the northern hemisphere. It's attached to the back carbon. It's going to be in the plane of the screen. So in our Newman projection, it's going to be attached to the back carbon in the northern hemisphere, and it'll be eclipsed with that front hydrogen, exactly like we would predict from a regular Newman projection. The other hydrogen is attached to the back carbon. It's in the southern hemisphere, and it's in the plane of the screen. So it'll be attached to the back carbon. It'll be in the vertical axis, and it'll be eclipsed with the CH3 group, and it'll be right here. So when we draw a Newman projection for sp2 hybridized atoms, when we're looking down that sp2 hybridized bond, everything is going to be perfectly eclipsed and everything is going to be perfectly vertical. And again, that kind of makes sense if you reorient yourself to look at it from the left. That carbon number 4 CH3 group is blocked by that hydrogen that's closer to me. It's eclipsed with that hydrogen that's closer to me. The rules would be the same if only one of the atoms was sp2 hybridized. We would have one that has a perfectly vertical Newman projection, and then the other carbon would just be its regular Newman projection. And that's looking at Newman projections for sp2 hybridized atoms. All right, let's do it. Ninja level 5 is looking at a Newman projection of a chair structure. How do we look at a Newman projection of a chair structure? Actually, we're looking at two Newman projections for a chair structure. We're going to pick two bonds on opposite sides of the chair, and we're going to cite down both of those parallel bonds at the same time. There are three options you could choose from. You could choose to cite down the 1, 2, 5, 4 bonds simultaneously, or the parallel 2, 3, 6, 5 bonds, or the 1, 6, 3, 4 bond. It doesn't really matter which one you choose, except for one principle. It really helps if you can find two opposing CH2 groups that are completely opposite each other in the chair structure. Here, I see that carbon 1 and carbon 4 are both CH2 groups with no other substitution. For these Newman projections of chair structures, it's best to leave carbons 1 and carbon 4 out of the Newman projection. Do not include them in the bonds you're citing down. That would leave us only one choice to cite down the 2, 3, 6, 5 bond for this Newman projection. So we reposition ourselves to the side of the molecule with two pairs of eyeballs looking down these chosen bonds. This is going to end up being kind of a double Newman projection. As a double Newman projection, we're going to end up with two dots and circles. We'll start with the dot and circle for the carbon on the left. If I'm looking at the molecule from this side, it's going to be carbon number 2 that's going to be on the left side of this Newman projection. The other front carbon will be carbon number 6 in its own Newman projection off to the side. And these two Newman projections will be connected by this carbon number 1 spacer. That's why we chose the CH2 group to be the spacers for these Newman projections. What I notice is that carbon number 1 is angled down relative to carbon 2 and 6. So starting from carbon number 2, I'll draw a bond down, that's carbon number 1, and then a bond up, and this will be carbon number 6. And carbon number 6 will be the start of its own second Newman projection. Behind carbon number 6 is carbon number 5, and carbon number 5 is connected to carbon number 3 through carbon number 4 as a spacer. And carbon number 3 is the behind carbon for the other Newman projection. So the back carbons, carbon number 5 and carbon number 3, will be connected by the carbon number 4 spacer. And the carbon number 4 spacer angles up, so when we draw it in the double Newman projection, it is going to angle up as well behind the Newman projection, connecting carbon number 5 to carbon number 3. Carbon number 1 could have been pointed up and carbon number 4 pointed down. If this was a chair flip, we would have gone through the same process, but the front spacer would have been pointed up and the back spacer would have been pointed down. Now we can add the rest of the groups. We'll start with the OH group on carbon number 2. It is an axial group pointed straight up. When I look at this molecule from the left, it's going to be pointed straight up into the northern hemisphere. It's attached to carbon number 2, which is the front carbon over here. So straight up from carbon number 2 will be this axial OH group. The other position on this Newman projection will be that hydrogen, the equatorial hydrogen on carbon number 2. The nitrogen group on carbon number 6 is coming towards you in the equatorial position. Carbons 1, 6, and 5 are towards you as a viewer, so the nitrogen is pointing even more towards you as a viewer. So when I go to look at this from the left side, that nitrogen is going to end up being on the right side of my new Newman projection. It's going to be attached to carbon number 6, and it's pointing down to the southern hemisphere, so the nitrogen group will be here attached to carbon number 6. The remaining hydrogen on carbon number 6 is axial pointed straight up, so on carbon number 6, the axial hydrogen will be pointed straight up. We repeat the process for the back carbons. On carbon number 5, that chlorine group is pointed straight down in the axial position. Carbon number 5 is behind carbon number 6, so pointed straight down from carbon number 5 will be this chlorine group. The remaining hydrogen will be up here to the right. Notice that when we complete the Newman projection, we have the same 120-degree bond angles for all of our groups around the Newman projection, just like we would expect from a regular Newman projection. You can't have any weird bond angles. You can't put this nitrogen down to the right and this hydrogen like straight out to the right or anything like that. Finishing up with this bromine, carbon 2, 3, and 4 are the back carbons of the chair structure, so that bromine is pointed even further to the back in the equatorial position. So when I go to look at this molecule on the left, the bromine is going to end up on the left side of my new Newman projection, and it'll be here attached to the back carbon, carbon number 3, which is behind carbon number 2. Now that I have the bromine and carbon 5 in place, the last stick must be down here in the back carbon, and it must be the axial hydrogen on carbon number 3, and that is in fact what we would see. Carbon number 3, axial hydrogen points straight down, so the axial hydrogen on carbon number 3 also points straight down. And this is how you draw the double Newman projection for a chair structure. Whew, we went through a lot of complicated Newman projections in this video with a lot of intricate scenarios, but now you have the tools that you need to be a Newman projection ninja.
I'm glad you're here with us for this training today. Check out these other videos in my playlists to see if there's anything else that can help you level up your ninja levels even further. As always, don't forget to like and subscribe.